start now. Hello, everyone, and welcome to this talk. I'm Arkadeep Mitra, an undergraduate student at the Indian Institute of Science, Education and Research, Kolkata. I'm also a KVPY fellow and a NIUS physics student at HPCSE TIFR. I'm very thankful to the SQIL team for inviting me to host the first episode of SQIL Science Symposium. And today we are going to talk about the reality of reality. Have you ever looked up at the night sky at this vast pool of massive and energetic objects and contemplated about how small and tiny our world of perception seems in comparison, and how difficult it is to comprehend their magnanimity, how much and how little we know about them? If you have, you are one of the many bright minds who, since the inception of the human race, have wandered in awe at the universe and tried to unravel its secrets. This knowledge and belief about how our universe behaves is what constitutes our reality. For example, if you are in a dream where everyone is walking upside down, then for a moment, as long as you're in that dream, that becomes your reality. But that is very specific to you, the individual. Collectively speaking, for the entire human race, our knowledge and belief about how the universe behaves is based on what we perceive through our five senses, our day-to-day experiences. And we form theoretical models to explain these observations and make predictions. For example, if you take a television set and throw it from a cliff, don't blame me if your parents accuse you, but if you think of doing it anyway, then your intuition about reality and at the same time our theoretical models predict that it will go down and not up. But things are not so simple, and reality is a matter of great debate and philosophical controversy. And there's so much confusion surrounding this that we don't even have a single definition of reality that everyone agrees on. In this talk, we'll make a journey through time and attempt to understand how, over the years, startling discoveries about the universe and revolutionary theoretical models have shaped our perception of reality. And we begin our journey at around 70 to 75 BC, when a branch of natural philosophy called alchemy began to originate. And at the heart of alchemy was this idea that base metals like mercury or gold or lead could be turned into gold. And among the many mythical objects in alchemy was the philosopher's stone, which I'm sure you must have heard of in Harry Potter, right? So alchemists believed that this philosopher's stone had magical properties. And if you would touch the philosopher's stone on base metals like mercury, lead, it would turn them into gold. Now, alchemists made a lot of important discoveries. In fact, they were the earliest to contribute to chemistry and eventually give birth to modern chemistry. One of these many startling discoveries is the one depicted in this picture. So it was a night in Germany, 1669, and there was this man named Henning Brand who used to practice alchemy. He took a lot of urine and evaporated the liquid by heating the urine. Then he took the residuals and heated it in a container until the container became red hot. And then something extraordinary happened. Fumes began to glow and come out of the container, and a liquid that glowed began to drip out of the container. He could collect the liquid, and even as it cooled down and solidified, it began to give off a pale glow. Now, this man thought that he had discovered the philosopher's stone, but this was actually the first discovery of phosphorus. So the phosphates in our urine that remained in the residual reacted with components in air when heated, like carbon dioxide, carbon monoxide, etc. And that gave rise to elemental phosphorus, which is what glowed when hot. Now, many people like Henning Brand tried for hundreds and hundreds of years to find a way to turn such base metals into gold or to find the philosopher's stone, but they never succeeded. And it sounded like an unrealistic and almost impossible idea back then to the masses and even to the educated people who often openly ridiculed them. But today we know that this is something that happens all the time in the universe. And the technical term for this is nuclear transmutation. That is the conversion of one chemical element into another. In nature, this mostly happens inside stars during fusion. So a star is composed of hydrogen primarily. And if the star is large enough, then in the interior layers where temperatures and pressure are exceedingly high, the hydrogen fuses to give rise to helium. And again, if the star is large enough, helium in the interior layers fuses to give rise to carbon. And this process continues sequentially provided the star is large enough to support all of these steps, and it stops at iron. Now the elements in between the elements shown in this sequence and the elements after iron are formed if the star is large enough during the death of the star, which is accompanied by an explosion that is spectacular. And we call this a supernova. This is an image that is obtained by stitching together several images taken by the Hubble Space Telescope. And this is an image of the Crab Nebula, which is the remains of a supernova. Basically, whatever remains after the explosion has taken place. And the orange filaments that you see here is hydrogen, which is the primary component of a star. And the blue light that you see at the center is due to electrons moving at speeds comparable to the velocity of light. And nuclear transmutation also happens elsewhere in natural and artificial nuclear reactions. And so the essence of this story is that, in some sense, stars are the philosopher's stone that we had been trying to find for so many years. And they had been lying right before our eyes in the sky, but we did not have the technology or the theoretical understanding to realize that this is not something unrealistic and impossible, but something that happens all the time in the universe. And next, we'll move ahead to the 17th century when the following book was published. And this completely changed the way we look at this world. Enclosed in this book were 4 laws that were so revolutionary that they make up most of our high school physics education even today in the 21st century. And I'm sure you must have guessed by now what I'm talking about. Let me know in the comments. The author of this book is Sir Isaac Newton. And the 4 laws that I'm talking about are the 3 laws of motion and the law of universal gravitation. And standing in the 21st century, it's a bit difficult to comprehend the revolution that I'm talking about. But at that time, people believed that everything in the sky belonged to the heavens, including other planets, the sun, the moon, everything that you see in the sky. And even today, we call them celestial, which literally translates to heavenly. Newton showed for the first time that the heavens are governed by the same fundamental laws that govern us, or even a grain of sand, which is an inanimate object. And he even derived Kepler's laws of planetary motion in this same book, which Kepler had earlier obtained empirically. So Newton made the unification of the heavens and the earth a reality. And this period marked the epitome of classical mechanics. Classical mechanics talks about the universe being deterministic in nature, which means that if you know everything about the classical states of an object right now, you will be able to determine using classical mechanics the states of the object at all points of time in the future with absolute accuracy. So if Mickey here knows the position, velocity, acceleration, etc. of the ball right now, and he knows how hard exactly he hits the ball, he will be able to determine with absolute accuracy the trajectory of the ball. This is what classical mechanics claims. And maybe Mickey will be able to tell whether it will be a goal or not. Uh, and Newton's contemporaries had immense faith in classical mechanics. Laplace, a very prominent scientist in the 19th century, went on to claim something that we call Laplace's demon. And the idea behind this is as follows. If there exists an intellect or a demon with infinite computational power and infinite knowledge about the states of all objects in the past or at a point of time in the present, then using his infinite computational power coupled with classical mechanics, he will be able to determine the states of all these objects in the universe at all points of time in the future with absolute accuracy. And this had very alarming implications that were a blow to the way we perceive reality. And one of the many prominent things that it implied was that the universe, the future of the universe is predetermined. And there exists nothing like free will or voluntary decisions for forms of life like human beings. And this was very, very alarming to us. But very soon, we began to notice various cracks in the theory of classical mechanics, various events that contradicted classical mechanics. And we had to come up with completely new theories to be able to explain these beautiful events that classical mechanics could not explain. One of the earliest realizations that we had was that the world is not completely deterministic in nature. And we found out that the behavior of very small objects is probabilistic in nature, meaning even if you know everything about the state of such a particle right now, you will only be able to tell me what the probabilities of the outcomes will be of the particle at a point of time in the future. But you won't be able to say with absolute accuracy what the state of the particle will be at a point of time in the future, even though you know everything about it in the present. And in the early 20th century, the work of many physicists culminated into the formulation of a new theory called quantum mechanics to explain the behavior of such objects. And this is an image of the fifth Solvay Conference in 1927, which was one of the many Solvay conferences which contributed a lot to building up the theory of quantum mechanics. And every person that you see here in this picture did remarkable and phenomenal work, stitching up all of which quantum mechanics was formulated. And every time I look at this picture, I cannot help but marvel at Marie Curie, this one woman sitting amidst so many male scientists in a field clearly dominated by them. And now we'll move ahead to exploring something called the superposition principle, which is a central concept in quantum mechanics. And we'll try to explore that through a thought experiment, the Schrödinger's cat experiment. And we imagine that there exists a radioactive nucleus which can decay. And this triggers a bomb when the radioactive nucleus decays. And we put this radioactive nucleus in a box along with a cat. And we know that when the clock strikes 12, there's a 50% probability that if you look at the box, you'll find that the radioactive nucleus has decayed, triggered the bomb, and the cat is dead. And there's also a 50% probability that when you look at the box, you'll find that the radioactive nucleus has not decayed and the bomb is not yet triggered. The cat is still alive. Now, quantum mechanics tells you that if you don't open the box, but if you close the box and you do not look at it, then when the clock strikes 12, the state of this radioactive nucleus is in a superposition of or an overlap of both the states of having been decayed and not having been decayed. And this is a very peculiar property, a characteristic property of quantum mechanical objects. But notice that here, the decaying of the nucleus magnifies to the cat being dead or alive. And so, when the clock strikes 12, if you do not open the box, then since the radioactive nucleus is in a superposition of both these states of having been decayed and not having been decayed, the cat should also be in a superposition of both these states of being dead and being alive at the same time. And this is something that confuses everyone, and this is a paradox. We do not know how to go about solving this apparent confusion because quantum mechanics does not apply to the realm of large objects like a cat, and we do not expect objects like a cat to abide by the superposition principle. And so now it is up to you to think about this and ponder that can you come up with a solution to this paradox. And while you think about it, I'll take one or two questions and then we'll move ahead after that. Okay, so we don't have any questions yet, and we'll move ahead, but feel free to ask any question along the way in the YouTube comment box, and we'll take all questions at the end of the talk, okay? Now to move ahead, we need to move back in time a couple of 100 years. And at around the 18th century, Newton and his contemporaries believed that light was composed of small particles called photons. But in the early 19th century, many scientists like Thomas Young demonstrated that under certain circumstances, light behaves like a wave. And this is a famous Young's double slit experiment performed by Thomas Young in 1801. And what he did is that he took a double slit setup where there are two slits and you shine light at the two slits. Light can pass through only these two slits as shown in this picture. And you shine light at the double slit setup and it falls on a screen that is some distance apart from the two slits. And what he observed is that we get an interference pattern on the screen. That is a pattern of alternate bright and dark spots as you see in the black strip to the right. And this demonstrates that light behaves like a wave in this setup because if you throw a multitude of particles at a double slit setup, then you expect the particles to either pass through the top slit or through the bottom slit. And on the screen, you expect to get two bright spots directly in front of the slits. But this is not what we observed in light. And I'll show you a beautiful simulation of how waves interfere with each other and forms this interference pattern on the screen. So light comes out from the two waves and the wave fronts from the two slits interfere with each other And as they fall on the screen, they form alternate bright and dark rings by constructive and destructive interference. Now, the interesting part about this is that some years later, we performed this same experiment with electrons, which we earlier considered to be particles. And we observed that if we throw a multitude of electrons at a double slit setup, and if the width of the slits is small enough, and if the distance between the slits is small enough, instead of getting a pattern like the one on the left, you observe an interference pattern, meaning that electrons are behaving like a wave. And this is something that confuses Goofy a lot, and this confused a lot of people at that time. This is the first time this experiment was performed in 1961 with electrons, and this was performed by Klaus Johnson, a German physicist. And the simulation that you see here was done much later in around 2001. And the white strip that you see here is observational data from the first time it was performed. And today we have performed this experiment with even large objects compared to an electron like Buckminsterfullerene or buckyballs, which are football-shaped molecules consisting of about 60 carbon atoms. And these are 1.3 million times heavier than an electron. And we have observed that in a double slit experiment performed with buckyballs, we observe the same interference pattern. And classical mechanics fails miserably to explain why we observe an interference pattern with objects which we classically consider to be particles. But quantum mechanics comes up with a beautiful explanation to why we observe such interference pattern with things like electrons or buckyballs. And now we'll look at another revolutionary experiment that was performed in 1887 by Michelson and Morley. And at that point of time, it was clearly established that light behaves like a wave in certain situations, as in the Young's double slit experiment. And all waves that we knew about at that point of time were periodic disturbance in some physical medium. And we had no observational evidence of any physical medium, the periodic disturbance in which produces light. But we hypothesized that since all other waves follow such a behavior, there must also exist such a physical medium for light, and we named that ether. The Michelson and Morley experiment boldly set out to test this hypothesis. And the setup that we have here is a light source that shoots light at a component that allows 50% of the light to pass through, and it reflects 50% of the light, both towards two mirrors. And light gets reflected at these two mirrors and comes back, hits this component and comes back to this detector. And if the medium is traveling with a velocity v with respect to this experimental setup in this direction, and the velocity of light in this medium is c, then you expect the velocity of light to be c plus v along this direction. This is the same as saying that the speed of sound in air is 340 meters per second, approximately. And if there's a wind blowing with velocity v along this direction, then the velocity of sound with respect to this experimental setup would be 340 plus v in meters per second. And since there's no velocity component along this direction, we expect the speed of light to be c along this direction. And this detector detects something that is related to the difference in time taken by light to traverse back and forth both these arms, the horizontal and the vertical one that you see here. And both of these arms are of the same length. And what we observed is that this detector detected with striking accuracy that there is no difference in time taken by light to traverse back and forth both these arms. And this could mean three things. That is, either the medium is stagnant with respect to the experimental setup. That is, this V is equal to 0. Or the medium also has a velocity component V along this direction. And it also has a velocity component V along the horizontal direction. And to test whether these two hypotheses hold true, what we did is that we performed the experiment 6 months later. And so if this is the sun and the earth is in a position here when we perform this experiment initially and moving in this following direction, 6 months later, the earth would be in a completely opposite position, moving with a completely opposite velocity uh, uh, when we perform the experiment 6 months later. And we observe that even when we perform the experiment 6 months later, there was no difference in time taken by light to traverse back and forth these two arms. And these eliminated both these hypotheses that V is 0 or there is a velocity component along this direction as well. And the only conclusion that we are left with is that no such physical medium exists, the periodic disturbance in which produces light. And this was very perplexing for everyone at that point of time, because we did not know that if a wave is not a periodic disturbance in a physical medium, then how do we even go about defining a wave? This is the original setup used by Michelson and Morley in 1887, and we call this an interferometer. And this floated on a trough of mercury so that no noise creeps into the setup and there is maximum accuracy of the observations. And many people tried to make small modifications to classical mechanics to try and explain why we observe such results, but they failed. And it was not until 1905 that Sir Albert Einstein came up with the theory of special relativity that beautifully explained these experimental results. And around 10 years later, Albert Einstein came up with the theory of general relativity, which predicted the behavior of objects having large size or large mass, like large stars or large planets. And this presented gravity as a geometric consequence of four-dimensional curved space-time. And this was something extremely different from gravity being thought of as a force according to classical mechanics. And so we set out to test whether general relativity holds, and it took us several years, but finally we were able to observe certain events where gravity behaves in a way that is predicted by general relativity and contradicts the prediction of classical mechanics. And around 80 to 100 years later, Stephen Hawking and Roger Penrose did some remarkable theoretical work on general relativity and showed that a consequence of the theory of general relativity is the existence of gravitational singularities. That is, points in the universe where the gravitational field becomes infinite. And around this region, the gravitational field becomes so large that nothing, not even light, can escape from that region. And when we talk about this, something that all of us should ask ourselves is that what took them so long to theoretically derive something that is simply a consequence of the general relativity theory, which Einstein had proposed around 80 years back. And the reason behind this is that to get any remarkable theoretical results or observational results that completely change the way we perceive reality, it takes the cumulative hard work of hundreds of scientists working for years and years that finally culminates into such a result. And one of many such scientists who worked in the field of general relativity was an Indian scientist, Professor Amol Kumar Roy Choudhury, who was a professor at the Presidency University in Kolkata. And one of his theoretical works was the Roy-Choudhury equation, on which Stephen Hawking and Roger Penrose relied heavily, and built their theoretical work based on the foundations of the Roy-Choudhury equation. And even then, when Stephen Hawking and Roger Penrose presented their work, black holes were a completely theoretical concept. And we had almost no observational evidence of the existence of black holes. There were a lot of people at that time who did not believe in the existence of black holes, including a lot of physicists and mathematicians. But today, we are fortunate enough to have the first image of a black hole. And this is an image of the black hole in M87 galaxy. And this is a supermassive black hole. This was taken in 2019 by the Event Horizon Telescope collaboration. And the next slide is something that is so exciting that when I look at it even today, I get goosebumps. And this is an image that was released by the same collaboration, the Event Horizon Telescope collaboration, at the end of March this year, which is not even a month old. And this is an image of polarized light in the exterior ring of the same black hole. And this gives us an idea about the magnetic field lines that exist in the region surrounding the black hole. And before we end this talk, something that I'd like all of you to think about is that we have learned that small objects are governed by the theory of quantum mechanics, and extremely large and massive objects behave in a way that is predicted by the theory of general relativity. And these two theories are very different and predict very different behavior. Now, why is it that objects that belong to the same universe but differ only by size and mass behave in a manner that is extremely different from each other? And this is something that has perplexed scientists for years, and physicists have been trying to come up with a theory that predicts the behavior and interactions of all objects in the universe, a theory of everything. But we haven't been able to find one yet, and maybe one of you will be able to contribute towards finding a theory of everything. And the crux of the matter is that reality, to the extent that we perceive, is subjective in nature. And such a subjective reality is bound to change with time, as groundbreaking work every day deepens our understanding about the universe and enhances our perception of reality. In fact, a very interesting thing to note is that for any theory to be called scientific, which contributes to our understanding of the universe, a criteria that it must satisfy is that it must give you some scope to be proved false. And the formal definition of this is that it must satisfy Popper's theory of falsifiability, which states that a theory is scientific if and only if it is falsifiable. That is, it gives you some scope to be proved false. Okay. For example, if I tell you that all swans are white, and you go around the world and you find a black swan, then you can come back running to me and tell me that, look, I have observed a black swan and your theory is false. And so my theory gives you some scope to be proved false. And this is the idea of falsifiability. I would like to thank SQIL for providing me this wonderful opportunity to address all of you here today. And I would like to thank my friends Rudra Mukhopadhyay and Basil Salim, both studying at IISER Kolkata, who helped me with various aspects of organizing this talk. And Basil is also a member of the SQIL team. And I would also like to acknowledge my mother, who has made me the person that I am today. Thank you. I'll take questions from the comments right now, but if I fail to address any of your questions right now, or you have any question later on, feel free to reach out to me. So let me check if you have any questions. Okay, unfortunately, we don't have any questions. You only have a joke by Shourashish Kormokar, whether curiosity or uranium killed the cat, which is a popular joke about the thought experiment of the Schrödinger's cat. Okay, since we have no questions about the talk right now, we'll end this session. Thank you everyone for attending this session here today. And even if you have any questions later on, feel free to reach out to me.